So before we start, just a reminder, page 291, that's the current assignment that's due on Thursday. I will be doing a homework check on that day. Okay, I haven't done that in this class. I did it in the other class. I did it once, but not recently. So I'm going to walk the aisles and check your homework. Okay? You better be good if you've heard. All right. So yesterday we learned that there's a way to find the average value of a function over any interval, any closed interval. So we're going to just do a quick one here. So as you know, I like to do multiple perspectives. So let's draw a picture of this first, and then see what we're trying to ask, and maybe we can suggest a possible answer before we actually answer it. So what does it mean to find the average value of the sine wave over the interval from 0 to pi? Okay, what does that mean? Well, it means if we were to graph the sine function from 0 to pi first, so we all know what this looks like. And then it's not a circle, it's not a half a circle, and it's not straight lines, and the concavity has to be right. So we know that it kind of does this thing here. Okay, it's not a circle, it's not straight lines. It has this nice smooth concavity to it, which completes this pretty little wave. Okay. So if we only focus on that, and I say what is the average value of it, well, we just have to add up all those points and divide by infinity. Okay, which becomes the problem. Any guesses? What do you think the average value is? Say it again. 0.5? Doesn't 0.5 seem like a good answer? Okay. Okay. Turns out that it's wrong. But it was a good guess. That would be my first guess. Okay. And the reason is it actually hovers a little bit more above than it does below on that interval. Okay. It's a little bit more above than it is below. Okay. So let's find out what the actual answer is for this. So the general formula that we said yesterday looked like this. Said that the average value of a function, and notice this is kind of important here, it's the average value of f of x, okay, because we use f of x in the formula, okay, and it's on the interval from a to b, is 1 over b minus a multiplied by the integral from a to b of f of x. So that's the formula that we're using to find the average value. Okay, so let's do it. So what do we got here? Average value is equal to, notice this, I always do this, and I want you to always get in that habit. This tells me where I'm headed. I'm out to find the average value. Okay? So on this one, I'm going to go from 0 to pi, so it's going to be pi minus 0 times the integral from 0 to pi of my actual function, which is the sine of x. And now we just have to figure that out, and we can do this by hand now. Okay, we know how to do it multiple ways, but we have to be able to do it by hand. So that's 0 to pi. Now watch what I'm going to do here. We say then it's multiplied by, now that what's the integral of the sine of x? Negative cosine. So it's negative cosine of x. And then evaluated from 0 to pi. And you have to get used to that notation. Okay, so this means, watch what I'm going to do here, negative 1 over pi times the cosine of pi minus negative 1 over pi times the cosine of 0. Okay. This is my f of b, this is my f of a, I'm subtracting those two. Okay, fill in the blanks. Negative 1 over pi, what's the cosine of pi? We're over here, right? Cosine is x, it's negative 1. Plus 1 over pi, what's the cosine of 0? 1. Okay. So I'm seeing 1 over pi plus 1 over pi, which is 2 1 over pi's. So it's 2 divided by pi. Yeah. I have to distribute. Yep. This whole thing is part of the function that we're carrying it out. See this 1 over pi? I can bring it in here. Okay, I can put it here if I wanted to. Okay, because it's a constant outside, I can bring it in. Or if you don't, if you're confused by that, think of it this way. I can say, oh, this is 1 over pi multiplied by, look at my brackets, negative cosine of x evaluated from 0 to pi. If you did this way, you'd say 1 over pi, and then it's negative cosine of pi minus negative cosine of 0. Same thing, because this is your negative 1, this is your positive 1, and it all matches up. What's in the orange matches what's in the blue. This one, we're just writing it on the outside and then distributing. Here, I'm just including it on the inside. So it works both ways. I can see you don't see it, but okay. All right. Bracket on the outside, then carry it out, then distribute. Works the same. 2 over pi. What's 2 over pi roughly? It's 2/3. Okay. So 2 over pi is actually what it is. So 2/3 would be maybe about right here. That's 2 over pi. This is my average value. Okay. And remember what the intent of this, the average value, means? That it's the magic height that creates the perfect rectangle that contains the same exact area as the area under the curve. Okay? So if you snip off this spot and you put it here and here, then it forms that perfect rectangle. Okay? Now, just to make sure we can do it, and we can prove it on the calculator, pull out your calculator, do exactly the same calculation, and get the same answer. Hi. Yep. Oh, yep. Okay, so you can write it however you want to. I chose to do 1 over pi. Notice I put it in parentheses, then multiply by the integral, and we get this answer, and 2 divided by pi is same answer. Okay, so this validates that this works for any interval. Okay. What's the average value of the sine function from 0 to 2 pi? 0. Okay, because the top half and the bottom half cancel each other out. Multiple ways to look at that. So that's the key. Notice to find the average, this is important, to find the average value of the function, whatever you do, don't take, well, I just have to take the first value divided by, and the second value, add them up and divide by 2. That doesn't work because we have to include all of the points in it, and this formula does it. Okay, so make sure you've got that right, and you can calculate that lots of different ways. Okay, switching gears now to the final thing that we have to learn in this section. Okay, so let's go do that. So we might remember that first semester contained a lot of work with derivatives. And I think I even said we're going to find the derivative of any function we can get our hands on. Right? Well, I've thought of a new function. Okay. What is the derivative of f of x is equal to, f of x is equal to the integral from 0 to x of t squared plus t dt. Just thought of a new function. The function contains an integral. What? That's what you were thinking. I know it's what you were thinking. Okay. All right, so let's explore. So let's explore this. What does that mean here? Okay. So let me ask you, what's if I say, what's f of 3? So we learned this. Wherever you see an x here, that's where you're going to put that number. Okay? So f of 3 is really the integral from 0 to 3 of t squared plus t dt. Right? So if you have a function that has an integral in it, it's kind of weird. And it's weird because there's actually two different variables. Okay? One variable corresponds to this, and the other variable corresponds to the variable that's in the function. So does it make sense that we would have to do this 1/3 t cubed plus t squared over 2 evaluated from 0 to 3? And that's what we've been studying. So to get this answer, we got this, and then we do this, and then we get some number. I don't care what it is right now. That's not the important part. Okay. All right, so then if I said, what's f of negative 2? F of negative 2 would be, well, that's the integral from 0 to negative 2 of t squared plus t dt. Now wait a second. That's 0 to negative 2. Isn't that going backwards? Right? But we know how to handle that. We don't have to go backwards. We can say that's the opposite of the integral from negative 2 to 0. Remember that? So if you swap the lower and the upper limit, then you take the opposite. So then again, we carry that out. It would be, the 1/3 t cubed plus 1/2 t squared evaluated from negative 2 to 0, which is again some number, some answer. We can compute it, but so this is how we can compute the answer to a function that contains an integral. We just plug in the number, we plug it in here, and then we carry it out, blah, 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 and we get to here. But what I'm asking is, how do we find the derivative of that function? In other words, what I'm asking for is, watch this, we know that f prime of x would be equal to the derivative with respect to x of the integral from 0 to x of t squared plus t dt. That's what I want. Yeah. Oh, I didn't carry out the negative. Yes, you're right. This one right here, negative. Yes, thank you. Everybody see that? That's good. Okay, now wait, look at this. What is the derivative of this function? Well, the derivative of the left side is f prime of x. The derivative of the right side would look like this. It's the derivative with respect to x of this. Now that's a whole lot of stuff going on there. Okay? Wait a second. What does the integral do? What do we do to this function? Find the antiderivative. And what does the derivative do? Let's find the derivative. And we end up where we started? Yeah, you think so. Okay. So let's prove it. Let's figure out what we get. By the way, does anybody know what time we end? 10:29 or something? Okay. $29. Okay. All right. Let's carry this through. You check me to see if I'm doing this right. So what I'm going to do is I'm going to handle this part first. Okay. I'm going to handle that part, and see the big brackets around that. I'm going to leave that alone. I'm going to wait to do the derivative after we integrate. Okay. So does everybody agree that that part in the middle turns into 1/3 t cubed plus 1/2 t squared evaluated from 0 to x? What I have underscored in the purple, that's just this. You do the integral, and then we're going to evaluate that. Well, let's take this one step further. Let's figure out what this is. So again, I'm going to leave the derivative until afterward. So this is, what do I got here? 1/3 x cubed plus 1/2 x squared. That's me plugging in the x. Minus, and then this is me plugging in the 0, 1/3 times 0 cubed plus 1/2 times 0 squared. Here. This is my f of, this is a, this is b, this is f of b, this is f of a. Can you see where this is going? Watch what happens. Well, this whole thing is 0, right? So we're out to find the derivative of 1/3 x to the third plus 1/2 x squared. Okay, you need your assistance. Derivative of 1/3 x to the third, x squared. Derivative of 1/2 x squared, x. So what is the derivative of a function that looks like this? The answer is that. And it looks a lot like that one, except what changed? The variable. Okay? Now I wonder if this works like all the time, or are there any exceptions? Let's go find out. All right, so let's pick another function. And then maybe if we can recognize a pattern, we could write our own rule. Okay. So I'm going to do another function with different letters. We'll see what happens. Let's suppose it's r of t, and it's equal to the integral from 4 to x of the sine of oops, I gotta go t here, and w dw. You gotta watch how I'm using the variables. You gotta put them, you gotta place them carefully. Okay. The variables matter. Okay, just a side note, okay? Don't copy this down if you don't want to. But if I said to you, hey, what is r of 5? What's the functional value of r? You see that this is where the t is. So it would be equal to the integral from 4 to 5 of the sine of w dw. Do you see how we're using this? The function has an integral in it, and whatever goes here is what we use here. Okay, so this would turn into, r of 5 would turn into this, just so you see where that's coming from. Okay, so let's see, what's the derivative of r of t? Well, it's r prime of t. Taking the derivative of both sides. And it's the derivative with respect to, what letter am I going to use here? T. If you look back at that one, it's the derivative with respect to t of the integral 4 to t of the sine of w dw. Okay. Well, I'm going to do this thing again where I'm only going to do the integral part first. So this is still the derivative with respect to t Okay, integral of the sine, we said. Negative cosine. So it's negative cosine of w evaluated from, did I put that extra back in there? Okay, I see what I did. Evaluated from 4 to t. And then when we're all done with that bugger, then we're going to find the derivative of it. Okay, what does this mean? Everybody here should know that that means we're going to evaluate it. So this is equal to d dt of negative cosine of t minus negative cosine of 4. Right? And I'm just going to clean that up slightly. Derivative with respect to t, negative cosine of t plus the cosine of 4. Okay. So we have successfully integrated the sine of w from 4 to t, and that's what's inside the brackets. Okay, now we just got to find the derivative with respect to t. What's the derivative of the negative cosine of t with respect to t? Sine of t. What's the derivative of the cosine of 4? 0. Why? It's a constant. The cosine of 4 is just a number. You know, it's a place on the unit circle. The cosine of 4, the derivative of that is 0. So, final answer is sine of t. So, once again, the derivative, I should do this one instead. This answer here is equal to this answer here. The derivative of this is that. Okay? Have you spotted a pattern yet? Let's see. So if I give you one, you tell me what the answer is. So if I say, what is the derivative with respect to x of the integral from 5 to x of t to the 4th minus 6t dt, what is the derivative of that integral? Yeah.
X to the 4th minus 6x.
X to the 4th minus 6x. Anybody agree? Okay, that is correct. Okay. Now wait a second. I've got a problem with this. Okay, that is the correct answer. What about this 5? Doesn't this 5 matter? Why not? Okay, does it make sense that this 4 right here ended up being this part right here? Right? So the derivative of the constant is always 0. Therefore, this poor guy doesn't impact the answer. Because the x part, which is the functional part, this is the part that matters. And that's where we get our derivative from, the constant doesn't matter. So, okay, I'm going to try to summarize this. General form. The derivative with respect to x of the integral from k to t, pardon me, k to x of f of t dt. Look carefully. The derivative with respect to x of the integral from k to x of f of t dt. Everybody plug it in where you think it is. When I say f of t, that means I can have a generic function. I can have any function. It just has to have t's in it. And k gets to be any real number. Final answer, f of x is correct. This is what's known as the second fundamental theorem of calculus. And you guys thought of it yourself. Yeah, there's more than one. Okay, do your homework. Trust me,